Hello again, we are in chapter 6, which is optimization of continuous functions, floating point functions. Unlike the combinatorial uh, problems and constraints that we had before, we can see that genetic algorithms can also solve continuous floating point number problems. And the first problem we're looking at, or the first function we're going to look at, is called the egg holder function, which has multiple local minima and maxima. We are going to look for the global minimum point, which is hiding somewhere there within a certain range of 512 by 512. And to do that, we use a genetic algorithm with a specialized, as you can see here, operations that are meant for floating point operations, and the individuals are made of floating point real numbers. And this is the actual function that we're trying to minimize in this case. So if you run this, we are going to find, as you can see here, this is the best individual is actually the solution that we're looking for. And that was a straightforward solution. Let's look at a more interesting function, maybe not such an interesting shape, but what's interesting about the Himmelblau function is that it has four points that are all the minimum points that have the same global minimum value, which is 0. And you can see it here from looking from above. These are the 4 points, and sometimes it's enough to find one of them, and sometimes you might want to find all of them. So if we run a very similar program to the egg holder, just changing the function, pretty much changing maybe the range, we will likely find one of them. And we are going to see here, here it is. Here we actually draw the four points where the minima, the 4 minima of that function, and we can see that one of them was found, and pretty much our solutions were concentrating around it. Some of them found at least the x or the y coordinate of it, are generally there around it. So that's good. What if we want to find the other solutions? So one way to do it is, for example, to go and change the random seed. We're using a particular random seed, so we can try 17, 13, whatever other numbers we like, and we are likely to find different solutions by doing that. What we're doing instead is a more interesting way to do it. We're trying to find all the solutions at the same time, and we're using the mechanism known as sharing or niching. It is explained in detail in the book, but the idea is we try to punish individuals when they are too close to each other. They have to share the bounty, so they're encouraged to go look elsewhere. They're not oblivious of each other. We also have to invert the function and to make it into a maximization rather than a minimization problem, because this is better, easier to share when we have a positive reward. So this also somewhat complicates the solution and requires the population size to be bigger, so it's not always practical, but when it works, it's very cool, for the very least. And we can see how it looks when we do that. So we're going to print the Hall of Fame individuals where they're going to be, and we're going to plot it as well. You see that this takes, we run it for a longer time because we have also the complexity of calculating the sharing between them. But you can see that this is the general population is a lot more spread than it used to be. And if we look at the Hall of Fame individuals, we see that the Hall of Fame, basically the best solutions nailed all the 4 points. We can also see it here. If we look at those individuals, we can see that all 4 solutions are pretty much represented here within the Hall of Fame, actually within the entire Hall of Fame. So that is a demonstration of using sharing and niching to find multiple solutions at the same time. We can continue now with the Simeonescu function, and we can see it here. This function is not particularly interesting other than it has this interesting boundary. So here this boundary is used as a constraint. We only want to consider the values inside that range or that constraint. And what you see here, the darker the colors are, is the lower the function is. So the two minima points, because of the constraint, are going to be exactly here and here. Otherwise, it would just be going to infinity. So we would like to find those minima points within the constraints, and we use for that, if we look at the program, we use a construct called feasible range. And here it is. So here we define so the constraint is defined within this feasible function, and it actually gives us something that's called the feasible range, which adheres to this constraint. And the toolbox of the DEEP can use it as a decorator for our function, for our fitness function, which is going to be the original function that is before the constraint. And the combination of two will actually help us to find the solution within this constraint. So if you run that, we can see that we found one of the solutions, which in this case it's the 0.8 minus 0.8, which is this. What if we want to find the other one now? So we now look at a different solution than before. In the previous problem, we tried to find everything together with niching and sharing. Here we can do something that is considered sometimes as sequential sharing or niching. We find one solution. Now that we found it, we can look for the second solution by using the first solution as a constraint, basically saying we don't want to go there anymore. We already found it. So we are actually, if we compare the second program to the first program, we will see that there is some distant threshold, but really what we did here is we took the feasible range that was defined before by the function itself, and now we added the area of the solution that we already found. We said if we are within a certain distance from that solution, this is not feasible, I don't want to go there, so we are not going to find this solution again, and therefore encouraging us to find other solutions. So if we run this program now, let's kill this. If we run this program now, we should be able to find the second solution, which you can see is the minus 0.808, which is this. So this is it for the real continuous function optimization. We'll continue in chapter 7, where machine learning is going to be the subject.